That many of you recognize this form is the form of what is called an even perfect number. Now, let me take care of some details here first. We're going to just give it a name because it's easier to reference it that way. But a perfect number is defined to be any integer k such that the sum of its proper divisors is equal to 2k. Okay. Now, this is actually the sigma function actually includes all the divisors, so that's why we have the 2k here. But in this particular case, 2 times k, if you look at this definition of k by laws of exponents, is just going to equal to 2p, 2 raised to the p where p is prime, times 2 to the p minus 1. Now, all I'm telling you is that's what 2k is equal to. We have yet to show you that sigma of any perfect number will meet this condition. Okay. Now, just let me write down just a simple example for p equals 1. For p equals 1, k, or no, sorry. Let's make it 2 since 1 is not a prime number. Okay. So p at 2 implies that k is equal to, if you put a 2 right here, you just get 2 right here. I mean, this whole thing will just be 2. And if you put a 2 right here, you get 3. So k would equal to 2 times 3 is equal to 6. Okay. Now, just notice by inspection here, or just, we'll just do this one simple one. Okay. This says the sum of the divisors of 6. Well, 1 is a divisor of any integer, so we start with 1 plus 2 plus 3. Now, notice that the definition of a perfect number is it's equal to the sum of its proper divisors. 1, 2, and 3 do sum up to 6, so that's what makes 6 the first perfect number. But notice that the sigma function expects all the divisors, so that's why you get this situation here is equal to 12, but that's equal to 2 times 6. So that's I remember when I first learned this stuff, it was slightly confusing. Why do you define it like this? But this is the definition of a perfect number. Okay, and it includes the part about the sum of the proper divisors equaling the number itself. Okay, now let's move along. Now, y'all, a couple of results that we're going to use to prove this result is the sigma of any prime number is just a prime number plus 1, and that's based on the definition of a prime number. For example, sigma at 13, 13 being a prime number, of course, is equal to 13 plus 1. Okay, so that's simple enough, right? So, and I just did this for specificity here. I'm using a lot of letters here, so I just explicitly call it a prime. Fortunately, it's short enough to do that. So that leads to the sigma of any prime is just the prime number plus 1, the simplest computation you can imagine. Now, sigma of any prime raised to a natural number power, what you would be getting here, folks, just to give you an idea, and I won't go through the whole thing, but 1 is always a divisor. Let me get that. The marker went away, it looks like. Okay, so you have 1 is always being a divisor plus p plus p squared. Add, well, this is finite, but it would be p squared plus, we'll include the ellipsis here, plus p to the m. Okay. Those are the divisors, and that's what sigma of p to the m is. But a lot of you will also recognize this as a finite geometric series, which has this as a sum. Now, I won't prove that's proved sometimes in high school algebra classes, more often than not, probably. But this is the formula for it, and we'll just use that formula. That's how you sum up a finite geometric series. Okay. Now let's keep moving. Now, so also something that's quite useful here is notice that the sigma function requires the inputs to be relatively prime before you can split it. Now, notice that this is definitely an even number right here. This is even. Now, notice 2 to the p minus 1 is necessarily odd, right? So even and odd numbers are relatively prime. They share no common factors other than 1. Okay, so that means we can split these two guys apart. Okay, we can split the two input arguments, and then we get, using both of these results directly above, we get this statement right here. Okay, notice that 2 to the p minus 1 is posited to be a prime number. So the sum of its divisors are just 2 to the p, 1 plus that. Okay, and then this part right here is just this formula. Okay, but notice this gives us exactly this right up here. Okay, 2 minus 1 is just 1, so I won't, but you notice that if you multiply, this is the result we got right here. Okay, for k. In other words, it's what we needed. This 2 times k is equal to exactly this, right, folks? It's equal to exactly this. Okay, and again, if I can write this out, but this would be equal to just 2 to the p minus 1, and then just times 2 to the p. And I'll envelop that in parentheses just to be safe. So that's times 2 to the p. Okay, so you see it's QED time. I thought it was kind of nice. Now, we did gloss over a few things, and you can't prove everything in the course of a 10-minute video, but this is something most of you should be familiar with right here. The sum of this object right here, it's a finite geometric series, is this, and also these two results here. This result here is very basic. And then the fact that you can split this thing if the input arguments are relatively prime is based on the fact every divisor of any of the arguments of one argument will pair up with another divisor. That's why you can multiply them out. That wouldn't be the case if the input arguments were not relatively prime. So that's kind of a brief wave your hand proof of why this is all true. But we have shown that this particular form, this even form, always satisfies the condition of perfect numbers. And in fact, many think it's the only form for a perfect number. They haven't proven that there's no odd perfect numbers, but most people who've studied it and looked at the numerical evidence don't think there's any odd perfect numbers. All right, so this may well be the only form that a perfect number can be in. So you know, it's manifestly even, but sometimes people forget to mention that. It's so obvious, but to be complete, sometimes you should talk about the form of an even perfect number, since we don't know if there's any odd perfect numbers. But in any event, that is it, folks. Hope you enjoyed. Let me know what you thought. If you want to see more detail, let me know in the comments. I try to minimize the detail just to get to the pith of the proof. But anyway, that does it. Thanks for viewing.